Hello everybody and welcome back. In this video solution, let's dive into the problem word search 2. I'm going to explain the solution in detail because it is a complicated one. There are multiple different components that we need to figure out before we can write the solution. Let's get started. The first thing you want to note is the word search 2 is just an extension of the previous problem, word search 1. And so we'll want to quickly go over it because there's one or a couple of things that we'll borrow from word search 1. And that is going to make our answer a lot easier to understand. Okay, so what is the problem description? We're given a board and this is just a 2D matrix of characters. And you're given one word that you have to search inside of this grid. In this case, let's say the word is ABCCED. So inside of this grid, inside of this board, you have to somehow search for the word ABCCED. At the end, you can return true or false, saying that, okay, I have found the word in true, or I haven't found this word. Now, we'll also want to discuss the solution. So, okay, what are we trying to do? Let's say that I give you a pen and paper, and on that paper is a giant board drawn, okay? And I give you this pen and I say that do whatever you want. Now, what would you do? How would you think about it in terms of brute force approach? Well, the first thing you want to do is you'll want to start and you'll want to find the starting point, which is the word of 0. Because you know for a fact that this entire string is going to start from the character A, you'll start looking for the character A inside of this giant board. And once you've found that character A, what will you do next? From that point, you can run a DFS and search in all the 4 directions looking for the next character. So we started off with the character A, and let's say that we were at this character A, okay? Now the next character is B, so since I have found the character A, I want to start looking for the character B, which is in the neighborhood of this particular A. So in this case, I find 2 neighbors S and D, and both of them do not match to the character B. And so I'll say that in that case, okay, you know what? It's no use to continue exploring in this case. I'll just return. So we'll go on and we'll find another A. Okay, great. So we found another A. Let's try to run a DFS from this point. And so we found this A. Let's try to look for the word B. Let's try to look for the character B inside of its neighborhood. So in this case, we do indeed find that we have a character B. And so we can move on to the character B. From this point, we want to look for the next character C. So we'll try to look for the character C in its neighborhood. And we do indeed find C, and so on and so forth. We can do the search for every single one of these characters. Now, we also want to talk about the complexity analysis for this question, because understanding that will lead us to a couple of observations that we can later exploit. Okay, first things first, complexity analysis. The complexity analysis in terms of time is going to be order of m, which is number of rows, times n, the number of columns, times 3 to the power of L. Now, there's a common misconception or a common mistake that people make and write it as 4 to the power of L. That is incorrect. And that's because even though it is easier to explain and understand that we're looking in all the 4 directions, it is incorrect logically. Because we're not looking in all the 4 directions. Because it does not make sense to. Look at this way. Let's say that we are at this character B. We have already considered the character A, and now we are at the character B. From this point, I want to start looking for the character C. Which all directions will I check? I'll check to the top, I'll check to the bottom, and I'll check to the right. I will not check in the direction to the left because I have already explored that. I've already considered A, and I don't need to consider it again. So in fact, there are not 4 directions that we're checking at each point. There are just 3 directions we're checking at each point. And we're doing this for every single character inside of this word of length L. And this is why you see the time complexity as this. The space complexity is going to be m times n, and this is just the height of the recursion call stack. Because in the worst possible case, you may have to explore the entire grid, so each of those values will keep stacking in the recursion call stack. Okay, I think we're pretty much clear on what word search 1 means. So now we can start to build upon word search 2. The first thing we note is that you're given the same board. Let's say we're given the same board. And instead of one word, we're given multiple words that we have to search inside of this grid. So let's say the word was ABCCED, and now we have to search a couple of more words like SEC and so on and so forth. For each of those words, now we want to return this true or false signal. And at the end, we want to return this giant list of all of the words that we were able to find inside of this grid. Okay, what is the time complexity going to be? Expanding upon the previous solution, expanding upon the previous brute force solution, this brute force solution will give us a time complexity of W times what we saw before. All I'm trying to do is, I'm just going to pick this word and I'm going to do word search 1 again. Then I'm going to pick the next word, I'll do word search 1 again. So on and so forth for each of those words inside of the word list. And that is why we have W over here, which is the length of the words. Now this clearly does not look too good. In fact, if you write and type out this brute force solution, as I've mentioned in my blog down below, it will give you a time limit error. And especially in Python, it will most definitely give you a time limit error. So we want to optimize that. We want to start to figure out something that can get us a better time complexity. Space is still fine. We're not messing with space. Time is the issue. So observations. As I always suggest, it's a good idea to look at a couple of small basic cases and build on top of that. But this question is complicated. And the question we want to ask first is, what are we looking for? I don't know what I'm trying to optimize. So let's instead zone in and zoom in onto this W thing. Because earlier we had this m into n into 3 to the power L, which seemed to work fine. But now we suddenly have this W added. Can we optimize this W? And so W is just a list of these words. So we'll try and see what we can find inside of this list of words. And now let's look at first case. We had ABC, CED, and we had SEC. So nothing really special over here. Let's keep on iterating. Let's keep on finding new cases. Let's say that we have ABC, CED, and ABC. What do we observe over here? In this case, the string ABC is repeated again and again in both of these cases. ABC ends with this, and like ABC is the entire string over here, and ABC is a substring in this case. So maybe we're looking at substrings, or maybe we're looking at a dynamic programming approach. It's very hard to say at this point, and maybe DP will be very complicated to implement, so we'll keep that aside for now. Let's keep on finding more cases, and let's look at this case over here. Let's say that we have the case AAAB, AAAC, AAAXD. What do you observe in this case? All of them start with the same AAA, right? And after AAA, we have a B in this case, C in this case, and X in this case. It looks like maybe dynamic programming is something we have to do. Or maybe not. Let's actually look at a visualization of this and maybe we'll understand it better. In this case, I have sort of designed this structure over here, and these are the strings that we want to search. And let's say the grid itself has these kind of structure. The grid is sort of optimized in this way. And so we have AAA, and we do find that AAAB exists, AAAC exists, and AAAXD exists. What do you also observe? As I said before, it looks like there is a repetition of these AAA characters. And so it would be a good idea to have this information. Okay, you know what? These prefixes are being repeated. Prefixes. Prefixes as the idea that we've just previously seen yesterday in the question implement a prefix tree. Can we exploit that over here? Yes, we can. If you observe, if we can somehow compress the information of all of these AAAs into AAAB, AAAC, AAAXD, then we can more easily find what is the remaining part of those characters, remaining part of those words. And so we are looking at a solution which involves prefix trees. Now, if you don't know what they are, you can refer back to my previous video, but I'll also quickly go over a couple of slides that will help you understand how we're building this Trie data structure. Let's say that we have the word AX that we want to add. This is a completely different example just to demonstrate the use of prefix trees. Let's say that we have the word AX that we want to insert inside of this data structure. So we'll create A as a node on itself. We'll split it out character by character, and we'll have A as the first node. Then we'll have X coming as a child of this A. And so we'll make X as a child of A and mark X to be the end of the string, end of the word. At this point, we can start to add more words. So we'll have APP, and you'll quickly realize that even though we have this APP as another completely different word, both of these APP and AX share the same prefix A. And in this way, we have compressed the information just a little bit, but we can compress it even more. Let's take the case of apple now. Let's say that we want to insert this word apple inside of this data structure. And so you'll realize that we don't need to have this another pathway going, storing the word apple. We can just use what was previously there. Also note that I haven't messed around with this ending marker. This will still remain as is. APP does indeed mark the end of a word, what we have over here, and APPLE is marking the end of another word over here. Similarly, we can add one more word, say API, and so you'll realize that there's a lot of compression happening. There's a lot of efficiency in this data structure when it comes to these kind of problems. And in fact, I think it's a general node because you're looking at words and you're trying to search for words. Words itself should remind you or at least get you thinking about prefix trees. Let's add quickly one more string BB. And yeah, again, this is the hash thing is something I've explained previously why we need to have that. But now we have this entire data structure in our hand, which is able to store this compressed, dense representation of all of the words. And so I think we can first start coding up this node and tree, prefix tree. Okay, let's first implement the nodes and the trees because that's the more simpler thing. So we'll have a class called node, and this is a class storing all of the nodes. So what does a node have? Well, a node needs to have this character in hand as well as the ending word, which I'm going to set to false. And what it means is, look at this case over here. A node has three pieces of information. First, what is its own character, which is in this case A. Second, who all are its children, which is represented by the green lines. In this case, it's X and P. And third, if it is an ending character or not. If this particular character marks the end of a word or not, right? And in this case, you see that X here marks the end of a word, which is AX. Let's implement all of these three. We'll say that self.c equals to C. We'll have another child. We'll call it a dictionary. And we'll store all of the children in here, which are represented by the green lines. And we have the self.end equals to end. We'll say that, end equals to fall by default because most of the characters are not ending characters. Only some are, and we'll specify that differently. Okay. Now we want to write the class Trie. Okay, we'll go ahead and initialize that. We don't need any extra parameters, that's fine. And we want to specify the root to be a node having this character hash. This is the character hash and this is the root of the trie. Okay, we also want to have this ability of adding words. So add word, self, and the word. How do we add a word to this data structure? Well, we want to first split it out character by character. We'll do that and we'll do some computation. We also want to be able to go over all of these characters one by one. So we can't mess with the root. So let's just create a copy saying current equals to self.root. And this current is, what is this current going to do? This current is going to, let's say that initially current was here. Then the current will move on to this character A. And then it will move on to this character X. So I want to have current equals to the current of child. So current.child over here and the character C. Now it's not always necessary that we have this dictionary character set up. So we'll want to do that. So if C not in current.child, let's create a node for this. So we'll have current.child of C equals to a node, equals to a node with the character C. I think this should work. And then we'll have, at the very end, we also need to be able to mark these ending characters, saying that this end marker signifies the end of AX word. So we'll say current.end equals to true. Once we're done with the iteration of all of the characters, we'll just set current.end equals to true. Okay. We're finally done with the code of this tree data structure. So now we can move on to the second part of the solution, and we'll actually talk about how to extend word search 1 to word search 2. It's going to be a very simple change in perspective. So let's get started. Okay, let's get started with the second part of the solution. This is a bit more complicated, but if you understand word search 1 properly, there are going to be a lot of parallels that you can drive into word search 2. Okay, let's start from the very basics, which is the search function. The search function previously had x, y, and I. X represented the x coordinate, y was the y coordinate, and both of these specified where we are inside of this board, what character we are currently looking at. The I was the very special index, which told you where you were inside of the word. X and Y told you where you were inside of the board. I told you where you are inside of the word. Because remember, in word search 1, we're looking for a particular word. And the function search returned a true or false at the end, saying that yes, we found a word, or no, we did not find the word. And the generation case of like exploring in all the four directions by the way, was looking up, down, left, and right. As simple as that. Now, if you understand this well, the word search 2 solution is going to look extremely similar. The function search is still going to have this x, y, and current. Now, this current is very similar to the I. X and y x and y simply mention where you are inside of the board as before. The current mentions where you are inside of the trie data structure. Previously, we were only considering one word. The word search 1 was only looking at one word. But since this is word search 2, we are looking at multiple words. We learned how to store that in a compact representation, a data structure called trie, a prefix tree. And current specifies where you are inside of that data structure. So very similar in ideas. There's going to be one small implementation level detail that we have to add later on, but that's very easy to understand. Then we have returning. Here we're going to return true or false, saying that we could find this word or not. In this case, we have to return none because things are a bit more complicated. It's true and false for every single word. So that's not exactly easy. Instead of returning anything, we can just store all of the words that match. All of the words that we were able to successfully find, we can store all of them and we'll return that at the end. The generation case is going to be exactly the same. We are again looking at up, down, left, right with 3 to the power L complexity, whatever. And with that being said, we can jump onto this coding up the search function with x, y, and current values. The first thing I like to do is get started with checking whether these x and y's are present inside of the bounds. So we'll say x should be between 0 and m, where m is the number of rows, and y should be present between 0 and n, the number of columns. Now, if that happens to be true, if both of these x and y's are inside of the grid, then that's good. That's what we want. But if that is not the case, but if any of them step out of the grid, we can return right away. And what do we return? We return none. We return nothing in this case, as we saw before. Okay, once that is handled, we can move on to first extracting out the board of xy. So we'll get the character we are looking at. So this is the character C. Now here is when things start to get a bit more interesting. Let's look at this visualization over here. Let's say that this hash is the current. We are sitting at the root right now. This current only has two valid children, A and B. And so the question we want to ask is, whatever the current board of xy we're looking at, whatever the current C is that inside of this valid children range or not? So we'll write it out saying that if C in current.child or not. Recall how current.child is a dictionary over here, which we fill in with the appropriate values. So if the C is inside of the current.child, which means that the character we are looking at is inside of the data structure. That character is inside of this giant tree data structure. And that means that that is good. That is what we are looking for. But if that is not the case, if this character is something else, something entirely else, then we don't have to even consider it. We can again return nothing. We can say, you know what, if you're not inside of the valid children, if you're not a possible valid child, then I don't care about you. You can just go away. Okay. What do we do now? As we saw before, this is the part of backtracking. And so we'll set the board of xy equals to be blank. And we'll say that we'll mark this board as visited. Okay. At the end, we also want to do board of xy equals to c. So we are sort of, we have this character c saved beforehand, and so we'll reset it to c. And in between, we can have these multiple search functions. So this will go to x, y, and current. But is it going to be current? It's going to be current dot child of c. See, as soon as we go past this line 25, we have ensured that the current dot child of c exists, right? Because that is present in the dictionary, otherwise we would have returned nothing. So assuming that current dot child dot c exists, we can now set and we can move the current pointer to move forward. So let's say that the current character, the board of xy was a. And the next step what will happen is this current will move from this root node over here to this a over here. And similarly, the valid children will also move forward, and so on and so forth. It will keep on going. So we can do this kind of computation over here. Now this is something we'll go ahead and copy paste. We'll do x plus 1, x minus 1. Basically, we want to explore in all the 4 directions. You can also write a for loop for this, be a bit smart about this, but this also works as well. So what does x minus 1 mean? We're looking at the upward position, right? We have a cell and we want to look up from it. X plus 1 means that we're looking down. Y plus 1, that means that we're looking at the right hand side, and y minus 1, we're looking at left hand side. Cool. So if you realize, this sort of entire search thing is sandwiched between this board of blank and board of C. And this is what makes the backtracking work. If you're confused about this section, by the way, this sandwiching thing, feel free to refer to the link down below or the info card that should appear over here. Okay. Are we done? There's one more thing left to do. What is the base case? Like, when are we ending this? See, we are always returning nothing, but we also want to store these matches, right? We want to store all of the cases where we have successfully found a word. Now, how do we find a word? Just after this line, we can say that, you know what, since we found this current of child of C, is this also an ending word? Is this current character marking the end of a particular word? And if that is true, then we can do answer dot append word. Okay, but word? What word? There is no word inside of the search function anywhere. Okay, this is a bit tricky. What do we do about this word? How do we get this word? And so what we can do is, this is just one little change that we're going to make. We're also going to store whatever the path we took up till now. And so with this path, we can take the path previously there and we can add C to it. And this will be added in the answer. We'll also do this over here, send the paths over all of these guys and do path plus C. Cool. I think this looks good. Do we have any more things to do over here? I don't think so. Cool. Now we can finally do a quick setup of the basic variables we need. We have length of board and length of board of 0, the number of rows and the number of columns. We want to iterate over all of them. And for each of them, I want to start the search. So I'll go in and search of XY. Also, I want this current guy, which will store very soon, and the path. Path initially can be just an empty string. I also want this answer over here that stores all of the answers, and we can return this answer at the end. Also, we need to initialize the tree, so let's do that. So tree equals to trie is initialized, and then alright, we also want to add all the word. For word in words, trie dot, what is that, add word function, add word, the current word. Cool. So this is the entire data structure, by the way, that we are forming. I'll show you. This is the beauty of writing good code. We have sort of in those two lines, first initialized the try and then added all the words. So in those two lines, we have constructed this entire thing. So pretty cool, right? 2 lines and we're done. What else do we need? Are we done? Okay, we also want this current thing. So let's specify the current to be try.root, because this current will start from the root of the tree as we saw over here. Okay. Okay, so before we submit this, let's do one little mental check. We've put this answer as a list, but is it actually a list? Well, yes, indeed, we do want to return this answer list at the end, but should we store these answers as list or not? The thing is, there can be cases of duplication. Let's say that the entire grid is full of A's. Okay, there's a 4x4 grid full of A's. And the string that you want to search is AA. And that's the only string. Your code will return all of the single possible combinations of these AAs. What we want is just one single combination. So to prevent those duplication cases, let's create this answer not as a list, but as a set. And we'll do answer.append. Instead of this, we'll do answer.add. And in this way, okay, so we'll just do list of this over here. And in this way, we'll handle the cases of duplicates as well. So finally, we can try submitting this and just hope it works, because this is a long video. Cool, this works out. Okay, cool. So this is it for the problem word search 2, and I'll see you in the next video.